Good afternoon to everyone who have participated in this conference IEEE Sensors 2020. I would like to thanks to Mr. Chairman and organizer of this conference who have provided us a platform to share our research work with multiple researchers, scientists internationally. The efforts they have made it possible in such a hard time of pandemic COVID-19 are really appreciable. Myself, Farhan Mumtaz, I belongs to Pakistan. Presently, I am working with Wuhan University of Technology to pursue my PhD program in Information and Communication Engineering. Currently, I am deputed in the research group of Professor Yutang in the National Laboratory for the Fiber Optic Sensing Technology, Wuhan. Besides that, I have 9 years of professional experience with Huawei technologies in different fields. My current area of research interest includes optical fiber sensors based on multicore, sapphire, and ordinary fibers. Also, computational electromagnetic compatibilities, and scattering problems are my key research interests. My research work will be presented by the following presentation. At last, I wish you all the very best for the conference. Thank you very much.
Hello, Mr. Chairman and research audience of this scientific society. The subject of my presentation is Thermo-Coupled temperature sensor by 7-core multicore fiber structures. I will divide my presentation into 6 parts. The contents include introduction, sensor design and principle, testing system, simulations, the results based on experiments, and finally the conclusion. The introduction part that includes the optical fiber sensing using multicore fiber, that dividing into different categories that mainly include optical information, optical communication. While in the field of optical sensing, multicore fiber has a new paradigm of innovation in this world. In addition to that, the MCF constitute a viable platform for testing various physical quantities such as refractive index, temperature, strain, curvature, and so on. By means of multicore fiber, various applications have been developed in the field of biology, medicine, and chemical, although it is reliable and compatible with multiple devices and can be easily embedded in Mach-Zehnder interferometers and also Michelson interferometer configurations. The interference from the outer core of the multicore fiber makes an interferometer highly sensitive to the environment. In addition to that, a structure based on taper fibers, single mode, lead in, lead out. The proposed structure on ellipsoidal ball in line multicore fiber can also effectively produce an interference spectrum. This slide we are presenting sensor design and principle. Basically, we are proposing 2 different kind of interferometers. The first one is the Mach-Zehnder that is shown in figure A, and the second one is the Michelson interferometer that is shown in figure B. However, we also taken an image of our fibers cross sections that is recorded under a microscope, and the fiber parameters are also shown in below table. Although the fabrication of the sensors are quite easier, and we just need a splicer device with a control arc power to fabricate these ellipsoidal balls that are shown in both structure, and once we use the control arc power, our symmetrical ellipsoidal balls can be established and formed, and later on these symmetrical ellipsoidal balls will splice together with another control arc power of splicer machine. While studying the principle of the interferometers, the interference is main thing that is taken to the account. which is occurred due to the optical path difference between two distinct beam of light intensities. The total intensity of the interferometer, which is composite of our structure, that is center core mode and outer core mode, and the interference mainly consists of different interference tapes. When the effective refractive index difference of mth order interference tape will shift with the change of ambient temperature, then the relation of temperature sensitivity for a Mach-Zehnder interferometer that is proposed can be estimated as given in equation 1. Conversely, for the temperature sensitivity against Michelson interferometer can be estimated as given in equation 2. In this slide, we are presenting the testing system. There are two different kind of interferometers that are used, and similarly, we have used two different experimental setup for our proposed interferometers. The figure A is used for our SMS MZI experimental setup, and figure B is used for our SM MI experimental setup, which are proposed in our experiments. Simulation part, we can analyze that when light is launched from the single mode fiber lead-in, several higher order modes are excited as the light passes through ellipsoidal ball junctions. Most of them will degenerate in intensity due to the phase difference across the multicore fibers cores. The input single mode fiber light intensity can allow only two dominant supermode to propagate in MCF, which are given in figure A and B, whereas such modes can be generated with the assistance of cladding mode, which is given in figure C. Here, cladding mode will act as a facilitator of two dominant supermodes while propagating through the multicore fiber. The simulated electric field plots of such supermodes are also obtained by using COMSOL multiphysics software, which are associated with the center core, outer core, and cladding modes, as given in figure A, B, C respectively. Here we are presenting the result of experiments. In figure A and B, we can see that spectral evolution and linear correlation of both sensors that we have proposed. For the first sensor, SMS MZI sensor, it can be seen that we have achieved the sensitivity of 136 picometer per degree centigrade and 68.1 picometer per degree centigrade for a sensor length of 40 millimeter and 20 millimeter respectively. And similarly, for temperature sensor structures of SMMI, it can be seen from figure B that we have achieved the temperature sensitivity 65.1 picometer per degree centigrade and 70.6 picometer per degree centigrade for a sensor length of 10 millimeter and 20 millimeter respectively. In addition to that, these sensors are produce high quality transmission spectrum with a 12 to 15 dB fringe visibility and higher extension ratio. Also, it can be observed in the experiment, the extension ratio varies periodically with the wavelength. Here we are presenting the result of experiment for refractive index measurement. The sensors are found insensitive in the range of 1.333 to 1.354. Very small fluctuation of interference strips were observed during the experiments. These fluctuations might be caused by the external temperature error but not accumulated by refractive index change. However, the insensitive RI response and dip experimental data can be seen in given figure. In conclusion, two different principles of temperature sensors based on thermo-coupled multicore fiber structure are presented. The use of ellipsoidal ball configuration in SMS, MZI, and SM-MI structure has significantly improved sensitivity and interference strength. The sensors are well elucidated that such structure can be part of seawater and biological applications. Finally, I would like to thanks and acknowledge the efforts of my supervisor who given me strength, support and opportunity to present this work in front of such a big platform of IEEE. Also thanks to my fellows and colleagues who support me during research, and also acknowledge the financial support given by Major Technique Innovation Program of Hubei Province of China, National Key Research and Development Program of China, National Natural Science Foundation of China. Thank you for your attention. If you have any question about the research project, without any hesitation, you can contact me by the email as given. Thank you.